think we can get started. Thank you all for being here, whether in person or on Zoom. We have a great talk lined up today. I've seen it before, one of my favorites. The great thing about this talk is that it's not slides like a conventional, PowerPoint presentation. He has uses what's called a Jupyter notebook. Who's heard of a Jupyter notebook? Anyone? See a few hands. But the really nice thing, so Jupyter notebooks basically allow you to write code. In this case, I think it's Python. You can do other, coding, languages as well. But for Python, it's really nice because you can write code, but you can also do what's called like markdowns. You can document your code very well. So it's a nice way to present information and code and ideas. Very nice notebook that I think will be provided to the students so they can go through on their own at home on your computers. You shouldn't need too crazy of a software setup to install Python. Well, yeah, I've installed Python many times. You can ask me about it if you have questions. So yeah, I guess before I introduce the speaker, we'll take a second to take a few breaths and shake out the week. So let's all stand up, whether you're at home or whether you're in here. Do three breaths, maybe a little stretch. Let's reach our arms up above our head. Down, maybe move your hips, your arms around. Let's take one deep breath in. Exhale. We feel the ground beneath your feet. Maybe wiggle your fingers a little bit. Just get the blood flowing. Another deep breath in. Exhale. One more time. Inhale. Exhale. All right. So yes, we have Gabriel Perdue, or Gabe. I'm not sure which you prefer. Either is fine. Gabe got his PhD from Chicago in physics, I believe. Worked on, well, I just looked at your LinkedIn very briefly, but accelerator, a device for an accelerator, an anti-veto, basically some detectors that you need to have like a very fast detector to kind of like tell you when a fast particle comes through. It's like called a veto system, or so he helped design one of those during his PhD system and did a lot of simulation work. He was a postdoc fellow at University of Rochester, and that was all before coming to Fermilab in 2013 as an associate scientist. He's currently a senior scientist, so he leads a group at SQMS, which is I think some of you have seen over the tours or got a tour of the SQMS facility. Superconducting Quantum Materials and Systems is what the acronym stands for. So yeah, he leads a group here, does a lot of cool work related to quantum computing, quantum information, quantum algorithms. So yeah, feel free to, listen up and feel free to ask a lot of questions. And Gabe, you can take it away. I assume your mic's working and set up.
Sound okay? Do I sound okay off-site? All right. So yeah, as was mentioned, I'm going to deliver a lecture using a Jupyter notebook. It's being hosted by.
Hi, Gabe. There's one thing I forgot to mention. Sorry, before we start, there's 7 students that didn't submit their consent forms, either online and in person. So Marsha or Spence might get in touch with you. It's important that we get these so we can post the lectures online. We can't put them online until we get all of those forms. So you might be contacted about that. So just want to give you all a heads up.
Okay, awesome. So it's being hosted by a Google Colaboratory, so you actually don't have to install any software. You can get a copy of the notebook if you go to this bit.ly link. So just remember or write down 4724F4A. Then you can go later. You can go to bit.ly and you can use that shortened URL, and it'll expand it to the full one. You should get hang on. Should get this notebook. notebook being hosted on as a Google Colab, and that way you actually don't have to install anything. It's all running in the cloud. And there is actually a little tiny bit of software installation I have to do here, but it's not actually installing anything on my computer. It's installing on the virtual machine that's running somewhere. I don't know where Google has it running. And it just takes a minute to do that. And for Jupyter Notebooks, you execute cells with Shift, Enter, and then you can just kind of poke at them. They're very intuitive. There's lots of tutorials online if you want to learn more about how to do fancy things with them. The most part here, as long as you know Shift, Return, Shift, Enter to execute a cell, you're in pretty good shape. And you can mix, as was mentioned, code and Markdown. Use it, so it doesn't matter. So that's my train of thought there. Yeah, you can do all kinds of cool stuff with Markdown, like you can embed hyperlinks, you can embed images, you can embed whatever. It's a lot of fun for presenting and sharing information, and we're doing all kinds of. So okay, so I'm going to go through a bunch of stuff here on quantum computing. There's a part 0 that I'm not going to go through here, which is an aside on the quantum mechanical phenomena of entanglement and superposition. I think you guys have had like a quantum mechanics lecture. You know, you've heard of entanglement and superposition. Yeah, maybe. Okay, so if I include this in the discussion, we'll go long, but you can look at it later. It's just some background material on what entanglement and superposition are. So I'll leave that up to everyone to go through if you're interested. I'm going to instead do is just jump right into computation. So computation, I'm going to argue, is performed by physical systems. That's what computation is. I don't know if people have their own thoughts at what computation is. What is it? What does it mean to compute something? But I argue that it's simulation combined with interpretation. So it's manipulating a physical system in search of a result where the state the system ends up in lets us use an abstraction to represent a real problem, right? So think about an abacus, physical system of beads on sliders. There are some rules for moving these beads around, and if you follow those rules while you move beads around, you can interpret the new position of the beads as an arithmetic operation. The abacus doesn't know it added numbers, but we know how to interpret the states as such, right? And like this gentleman here is probably not aware that he's doing an arithmetic operation, or maybe he is. I don't know. Maybe he's doing he's calculating a tip at a restaurant or something. I don't know. But nonetheless, you can use these systems to do calculations. Okay, so but an abacus is slow. I mean, actually, some people are quite fast with them, and some people are really fast with them. But today we prefer electronic devices, right? So you got phones, laptops, these kinds of things. And to do computation with an electronic device, we first develop an algorithm, which is this set of rules that we follow in order to do a computation. Tell us, how we manipulate the system to get our result. And in particular, for electronic devices, we want to manipulate binary states, two-state systems, right? And then we simulate the operation by actually physically running currents and measuring voltages. We actually manipulate the physical system, right? And then finally, we interpret the outcome using our brain, which is simulating something, to get the answer, right? And so there's a little bit of philosophy here in terms of simulation and computation and interpretation, and how does this all fit together? And you might be wondering, okay, I thought this was Saturday Morning Physics. Why are we talking about computing in a physics class? So, but remember, I'm arguing that the computation is the simulation of algorithms by physical systems, right? And the only subjective piece is interpretation. So physics is computation, and computation is physics at the deepest possible level. Right, so that's the argument that I'm making. So it's actually extremely natural to study computing and quantum computing in a physics class, right? So if physical systems are used to simulate algorithms, are physical systems we aren't manipulating, simulating some algorithm? Absolutely, they absolutely are. So our physical universe is computing something, as we speak, it's computing something. The entire physical universe is involved in a calculation. Everything each and every one of us does is part of it. Now, how do you interpret these things? That's hard. But there's absolutely algorithms that are being executed by reality as we speak. So there's a school of thought in physics that is the bottom of our search for everything, right? Like we're always looking for what is the most fundamental set of rules and laws that govern the behavior of matter and space and all these different things. When we get to the very bottom, we're going to find only information theory, pure information theory. We live in a quantum mechanical world, so it's necessarily going to be quantum information theory. Right? So from this perspective, a quantum computer is like a collection of piano keys for an instrument that lets you play like the base layer of physical reality, right? It's like an API to physical reality. So that sounds like something that belongs in physics class, right? All right. So let's look at a couple of concepts from classical computing using the circuit model before we go to quantum computing to kind of set the stage. Okay. So there are a number of different models of classical computation. You guys should go off and read about them sometime. Go read about like the Turing model sometime. Like it's crazy, but you can do all kinds of wild stuff with it. I mean, you should go read about it just to get a trip. But one of the ways we can express computation classically is using this thing called the circuit model. And to explain that, I'm going to start with talking about adding binary numbers, right? So there's an old joke, you know, there are 10 kinds of people in the world, those who understand binary and those who don't. If you understand binary, you're maybe laughing at this joke. And if you don't understand binary, then you're wondering, you know, joke's on you at some level. All right, so to add two numbers with a computer, right, we first represent them in binary. And we do this because the system that's operating at the bottom of all of our electronic devices uses base 2 arithmetic, right? So we're used to base 10. Base 10 is what we do day in, day out. Base 10 numbers look like this. You know, you have things like this. And can you guys read that okay, or should I blow this up another level? So, you know, you just say 765 is 7 hundreds plus 6 tens plus 5 ones, where this is like 100 is 10 to the 2, the 10 is 10 to the 1, and the ones is 10 to the 0. So you're using 10 to powers to track your place in the base list. And of course, it's funny because we're so used to thinking of base 10 that I'm explaining base 10 using base 10, right? Like all these numbers are written in base 10. So I have base 10 on one side and base 10 on the other side. It's almost hard for us to not think in base 10 because we do it so much. I'm going to trust other folks to keep up with things in the chat if there's questions. Okay, so binary is a lot like this, right? Except that instead of keeping track of powers of 10, we're keeping track of powers of 2. So I have a binary number on the left here, prepended with this 0b. The 0b lets you know, okay, now I'm using binary notation, right? For hexadecimal notation, you use 0x. But anyway, so we say that this is 1 times 2 squared plus 0 times 2 to the first plus 1 times 2 to the 0. So adding up powers of 2, so this gives you 5, right? Because this is 4 plus 0 2's plus 1 1 is 5, right? So that's how you encode a number in binary addition, or excuse me, in binary. And so it's useful for computation, as I mentioned, because you know there are a lot of simple 2-level physical systems that we can manipulate very quickly. And to do addition, you just have to write down some rules, right? So there are some rules for binary addition. And so you can like look at a few of these and you can kind of work them out in your mind and see, okay, these sort of make sense in terms of I have some inputs and I have some outputs, and I'm expressing my inputs in binary, I'm expressing my outputs in binary. And you just start with this, right? And you can build up more difficult computations using these rules. So I can take this set of rules and I can use them to add 6 and 7. So you get your calculator and you type 6 plus 7. Way under the hood somewhere, something like this is going on. Those numbers are represented in binary. These rules are invoked for each column, and they tell you how to basically take all of the inputs and get these outputs. Okay, so far so good. And then we can check our result. Is 0b110 plus 0b111 13? It is. Python says it's 13. But that's expressing the answer in base 10. If I ask for that in binary, I can say, okay, give me the binary representation. It is indeed this 0b1101. So the joke that we had above is that there's really 0b10 kinds of people in the world. But of course, if you put the 0b in front, then you know it's not funny anymore. So that's binary addition. So how does that relate to the circuit model of computation? So once you have these rules, right? I've given you some rules. how do you implement them in hardware, right? I'm saying this is something we're going to do a physical simulation. Some physical system is going to represent that stuff. How do you do that? Well, humans have figured out how to use transistors to implement logic gates, right? And they're very fast. And we can represent those gates visually. We can reason about them using circuits where lines carry data, right? And gates, we call them gates, or these little nexuses or little vertices where interactions happen, right? And then we can use truth tables to show what happens inside of a circuit. So here are some classic circuits. So here's the NOT gate. So some data comes in, represented like this. There's a little NOT A. This is the truth table. A0 gets flipped. 1 is the output. If you put 1 in, you get 0 on the output, right? And A and B, so if you can look at the little truth table here, if they're both 0, you're going to get 0. If either one of them is 1 and the other one is 0, you get 0. If they're both 1, you get 1, right? So you've seen all these kinds of things before. Maybe you haven't seen the XOR gate before, the XOR, right? So this is exclusive OR. So this gives you a 1 only if one or the other is 1, but if both are 1, then it gives you a 0. So it's exclusive OR, right? Kind of interesting. Some of these composites are so popular, they're built as primitives. So for an example, the NOT AND gate, right? There's like its own little symbol combining AND and NOT into NAND, right? So it's not technically fundamental, but it's basically treated as fundamental. And there's the NOR gate. This is another thing. And so like if you look at, or if you take, if you do electrical engineering and things like that in college, you'll literally write these kinds of circuits out to do certain types of computations. I mean, you'll see this sort of stuff done, and you'll use these little symbols graphically to express what's going on, because it's just a convenient way to chart out computations when you're using the circuit model to do computations. Great. So now, how would we use these gates, right, these little circuits, to implement one of these rules for binary addition? Well, you can kind of see, okay, I got 2 inputs, and I got 2 outputs. And I need it to work such that if I put 0, 0 in, I get 0, 0 out. If I put 0, 1 in, I get 0, 1 out. If I put 1, 0 in, I get 0, 1 out. If I put 1, 1 in, I get 1, 0 out, right? So I need to combine a bunch of these little circuit elements to give me that, right? And this is a famous circuit made of an AND and a XOR called a half adder. And this is what it looks like, right? And so you can go and you can check, okay, if I put zeros and ones into this circuit where I expect them to be, right, then I'm going to get what I expect at the end. And this is a modular addition sign, by the way. So if it carries over, then it just goes back to a 1 or a 0. So there we go. There's the circuit for that one, and I encourage you to go, play with it. You can combine half adders and an OR gate to build a full adder, right? So that's how I get my 3 input, 2 output version of this. And again, encourage you to go check, like go plug little zeros and ones in and see if the right things come out the other side. And you can cascade full adders to add even larger numbers, right? So if you have 2 3-bit numbers, right, and you want to do this computation, it turns out the circuit looks like this, right? You have 2 full adders and a half adder, and that gives you the addition for those guys. So for fun, like I said, and not now, you should go verify that these circuits do the things that I claim that they're doing in terms of addition. And then I would encourage you to try to work out one for binary multiplication. So first, write down how you would multiply 2 single-digit binary numbers. See if you can extend that. If you need to worry about the carry, see how you would do larger ones, kind of assemble them together. And that's a sort of way of using the classical circuit model to implement an algorithm for multiplication, right? There's other things that you can do. I don't have it written down here, but another really easy thing to do with base 2 binary multiplication like this is shifts. So you move all the digits 1 to the left or 1 to the right. That's another very powerful operation. You might think about what that does, what a shift does to a number. Okay, so this is looking at software now at a pretty low level, right? It's not quite the bottom, because I didn't tell you how to actually implement a transistor logic gate or what a transistor even is. You can go Google transistors and read about them. But if you're willing to accept that I can lay out little transistors on some silicon microchip and then run current through them and they act in this way, then that's the level that we're starting at for computation. And you know, some of these people have been working on implementing transistor logic gates for a very long time, right? I mean, for more than half a century. And when you hear that a chip has 1 billion transistors or 57 billion transistors or whatever for some of these chips that are on the screen here, what that means is they've got like 57 billion of these little elements all set out in some way, and they're organized to make computation efficient and fast, basically. If you run electrical currents through them, they will churn out little answers. Little numbers go in, little numbers pop out in the registers. There you go, right? And 57 billion of these little elements lets you do pretty complicated computations, right? So, I mean, you can do a lot with these things. And you can lay on different types of abstractions, right? So we don't think about programming really at a high level in the circuit model, right? What you do is on hardware, you bundle together groups of these operations that you do a lot, maybe code them into directly, and then you start layering other pieces of software on top that operate with those representations, that operate with that circuit representation to give you a more and more abstract view of the sort of computation that you're doing until you end up with something like, you know, like this, like literally like this Python running in some cloud-hosted, you know, window of a browser, right? In principle, at the very bottom, you could code everything using only NAND gates, right? So that little not AND gate I showed you, you can go implement Microsoft Word, right? All the features, absolutely everything that you see there, all the way up through the bottom of the software stack up to the top, you can do all of it with NAND gates, right? So that's, you know, a lot of expressive power, right? So you can, in principle, compute anything like this, right? So there are some limits to classical computing, the sort of computing model that I've shown you so far, though. So, you know, I just said we can compute everything we went to under this paradigm. Is that really true? And the answer is that in some senses you can, but you have to remember that we're driving a physical system to run our algorithm. So there's some little piece of silicon, and we're running currents through it, and we're flipping registers, and there's a physical thing that has to move for every computation we're doing. There's some electrons that move around, something like that. So we have to have a physical system that can do this. And we're running it according to these rules. And so we could run into problems because there's a physical limit to how fast we can move these things around, right? So, and that turns out to be a big problem because you can write down an algorithm, right, to solve some problem. But if it requires like the lifetime of the universe, for instance, to actually run the little electrons around, you know, you haven't really solved it, right? That's sort of like on, you know, your homework. If the teacher asks for an answer or some answer to some question, and you say like, well, people know how to answer this, right? That doesn't cut it, right? Like you have to actually give the answer for it to count, right? To have actually practically solved the problem, right? So we might be able to tell someone algorithmically how to build some crazy chemical compound that could maybe cure cancer, but we can't actually tell them what the molecule actually is, right? And so that's a problem, right? Like we haven't really solved the problem. Okay, so just to get some sense for like how difficult that problem is of like thinking about building molecules and testing properties of chemicals and things like that. So suppose that you wanted to do a simulation of a molecule now to compute some chemical properties, right? Like protein binding affinity or toxicity in humans or something like that. So the electrons in a molecule are two-level quantum systems, right? And this means that in order to write down the physical description of the electrons, we need to use superposition and entanglement. Now, I skipped the part about superposition and entanglement at the beginning because, as I said, we won't have time if I go through all that in detail. And I've included it in the past for when I've given versions of this lecture to more junior audiences. But if you're gonna have to, if you just don't remember anything about superposition and entanglement, then you just have to take as a statement of fact that the number of states in a system of n entangled particles scales like 2 to the n, right? So if you want to start just writing out the number of ways that you can combine and write down the different states for your set of particles, and you start with 0 and then 1 and then 2 particles and 3 particles and 4 particles and 5 particles, you're going to see the number of little things that you have to write out is growing exponentially. And at each step, it's doubling, right? And so it's growing like 2 to the n is what the scaling is, right? And so if we're talking about a molecule, n is the number of electrons, right? So imagine we have 50 electrons in our molecule that matter for its chemistry. If one number is a byte, 8 bits of precision, and 50 electrons would require how many gigabytes of memory? So that's 2 to the 50, and then I'm going to translate that into gigabytes. and you come up with 140,000 gigabytes of memory just to write down what the state of this 50 electron system is, right? We haven't done anything with it, we're just writing it down. So that's roughly the scale of a world-class supercomputer. So humans can do this, right? But suppose you come up for a new idea with a molecule that has 100 important electrons, which actually still is not a very big molecule. So 2 to the 50 is one world-class supercomputer. How many world-class supercomputers is 2 to the 100? And it's 1,000,000 billion supercomputers, right? So our civilization has like 3 computers of this class, right? So 1,000,000 billion of them seems like kind of hard, right, to pull off, especially with their networks to share memory and all that kind of stuff. And what if we want even more electrons? What if you have an idea for 150 electrons or something like that, right? I mean, you know, you can see how this is running into big problems. And you know, one of the big issues is that the computational devices that we're used to using, which are these transistor-based implementations of logic gates, have to brute force the calculation of superposition and entanglement, right? Those aren't native operations for the physical system that we've chosen to do this computation. And those costs scale exponentially with the size of the system, right? So we have to run them much faster, and we need them to run a lot faster. We need many more of them, right? So you've heard of Moore's law, and I think I mentioned that again in a minute, which is this idea that number of transistors that you can fit on a chip doubles roughly every 18 to 24 months, something like that. So can we just wait for the point where we just have piled on so many transistors that we can just brute force our way through this? And the answer is, well, you know, maybe, but not really. You know, we're running into limitations on Moore's law, right? So for about 5 or 10 years, people have been saying Moore's law is dead, and it keeps surviving. So I'm not going to call it dead yet, right? But there's a lot of skepticism on how much further it can operate, right? So we're down to sort of like, I think 3 and 1 nanometer spacings basically between transistors now. And if you look at Intel's roadmap, it goes out to 1 angstrom at this point. And this is starting to get really close to single atom sizes, right? So you're not going to go farther than that. So we've got a few more generations of Moore's law, but it's not some arbitrary runway of Moore's law going off into infinity, right? And then there's a more serious problem that you don't hear about a lot that comes from something called Dennard scaling, which basically tells you that the energy density grows exponentially with these transistors. And that makes sense, because as you're packing in twice the number of transistors, you need twice the amount of energy to run it. And so we have already hit the point where you can't turn on all the transistors in a chip. If you turn on all the transistors on a chip in your phone, it will melt. It just melts on the spot. It will destroy itself, right? So even if you have a lot of transistors, you can't use them all, right? And this is one reason why, if you pay attention to like microelectronics and these kinds of things, all you guys are all so young. I mean, so when I was your age, you know, computers, you basically had a CPU that just did everything, and it was very fast, and it was a general purpose processor. But these days, what you have is if you look at the system on a chip in your phone, there's 10 different types of microprocessors, each of which is highly specialized to different tasks, right? And this is how people are managing this complexity and these problems with the scaling, is that you have to hyper specialize your little chips, right? So you keep coming up with clever ways to deal with it, but there's serious limits, right? And so here's some graphics showing problems with like, okay, transistor scaling is starting to tail off. This is an algorithmic comment I'm not going to get into a lot of detail on with parallelization. Energy consumption is a very big problem. Basically, power density can already melt chips. So our systems that we're using to do computation are really running into limits on the sorts of problems we would like to solve to do things like, for instance, computational chemistry. Right? So this is bad. Like, we need resources on scales that are ludicrously beyond our civilization, right? We need to go out, we need to convert entire galaxies into giant networked computers, right? If we're going to try to do these kinds of calculations that we're talking about. That seems a little out of reach, right? But we'd like to solve these problems, right? Like, cancer sucks, right? So we'd like to get rid of that. So what I'm going to argue is that we're using the wrong hardware to implement the algorithms that we care about here, right? So if we want to simulate molecules to look for new drugs, maybe we should build systems out of molecules themselves that scale more naturally to the problem, right? And that, at some level, is what chemistry is, right? Like, you can actually get molecules, right? And you can test things like what the protein binding affinity is. That's a calculation. You've computed, in some senses, you know, using an analog computer effectively, what the protein binding affinity of your molecule is. right? But you can't automate that. There's no API. You can't, you know, scan over algorithmic states like, or excuse me, molecular states like that, right? There's like each experiment is a very bespoke calculation. And then you need the stuff too. You need all the, you have to synthesize the molecule, and that's hard and it's very expensive. So what we want is we want some computational platform that will let us natively address these kinds of problems, right? And that's where quantum computing comes in, right? So there's a different approach to computation that deals with these problems. So I mentioned computing properties of molecules already. Why is this hard? Turns out the answer is that molecules are quantum systems. So superposition means you need a lot of digital numbers to describe them. The physics are just wrong for the computation we want to do, right? So what we really want to do is we really want to have a device that is natively quantum, that natively handles entanglement and superposition. If you do that, if you use quantum states instead of these classical two-level systems, then you can do a lot of cool things. And so the major difference is that now instead of using bits, a two-level bit of information is encoded in a bit, we have qubits. So a qubit is a quantum bit, and they can natively access superpositions of states, and they can natively be entangled in many systems, right? And so quantum computers map very naturally onto some of these types of problems, right? And I've already mentioned that there's exponential scaling in terms of computational difficulty for simulating qubits as this 2 to the n problem. So if you want to think about like what does a Commodore, if you want to simulate 10 qubits, you could do that on a Commodore 64, which of course is way before any of your time. So that's maybe a bad reference. But if you want to do 30 qubits, then like a beefy AWS instance can do that. The entire global computing cloud, if all networks together, can do about 60 qubits, right? So like there's a lot of computational power embedded in a fairly small number of qubits, right? I don't necessarily need 57 billion of these guys to do something super interesting, right? Relative to the kinds of things that we can sort of theoretically do now, right? So just as a quick aside, I'm hand waving a lot about why quantum calculations are hard. I'm sort of implying that entanglement is a key bottleneck. It's really not, so don't think that, but it's a convenient thing to just sort of like walk around with and talk to people about. It's not really true. If you want to really get into what's going on beyond, we can talk later, but it's a big digression, so I don't want to get too deep into that. I just wanted to have that parenthetical note. All right. So the manifestation of our machine now looks very different than what we're used to. So our computer might involve a set of spins and a register that we manipulate, right? So like a bunch of trapped ions, right, in some held in place by lasers, right? And those ions are now your computer, right? So I've got a bunch of this is the artist's rendition of a set of ions sitting here trapped by a laser, right? And we want to manipulate them from one quantum state to another, and that's how we're going to do our computations. Here's some photos of some real quantum computing devices. So this is the superconducting transmon. So it's a qubit technology, the superconducting transmon chip that Google built back from, this is, I think, pictures from 2019. At Fermilab, we're building a quantum computer using superconducting radio frequency cavities, which we originally built for using as part of a particle accelerator. But it turns out you can also use them as part of a quantum computer, right? So here's one of those cavities. This is a photo. You can't see the ions in the way it's set up, but this is what the device looks like from these ion trap machines built by a company called Quantinuum that used to be part of Honeywell. There's another device that uses photons. It's a photonic quantum computer built by a company in Canada called Xanadu. And, you know, when you get the thing, you can go look at. All pretty cool. When you see things about quantum computers, people often show pictures of dilution refrigerators, and that's because if you're using the superconducting devices, then you have to chill the chips down to very close to absolute zero. You use dilution refrigerators to do that, and dilution refrigerators look really cool, right? So people like showing photos of dilution refrigerators. And so here's a photo of a couple of Fermilab scientists working on a dilution refrigerator, you know, looking cool. You can go to, this one is from a company called Bluefors. I don't know if this particular one is. It might be from a company called Bluefors. You can go see, you know, look at more about dilution refrigerators. It's cute though if you go to the Bluefors website and you try to figure out, well, if I want to buy a dilution refrigerator, how much is it? And the answer to that question is, if you have to ask, you can't afford it. So, all right, so what are computers practically good for, right? What's the real killer app, right? So, I mean, there's a lot of thought on this and opinions. You can go look at a little slick video series of sort of like flashy videos from Microsoft where they talk about these kinds of things. But there are some things that we're sure they're going to be good for. And the number one thing, in my opinion, for sure, is simulating quantum systems, right? So we were just talking about these problems in chemistry, right? So for like all kinds of chemistry stuff, like drug discovery, it's gonna be very interesting there. Material science, again, for the same reason. Simulating really bizarre physics systems like black holes, nuclear matter, so on. We need quantum computers for this because these systems can really only be properly understood quantum mechanically. So from this perspective, a quantum computer is really a tool for discovery. It's like a telescope or a particle accelerator. It's not necessarily like a GPU card that speeds up some particular calculation for you, because they're going to really be good at particular types of calculations. Right? And so there was a meme after the Super Bowl. This was my participation in that meme. Not many meme fans here. All right. So okay. So now let's start getting into a little bit of math. So unlike classical bits, which can be either 0 or 1, qubits can be superpositions of these states. Right, so we can write down a qubit's value using a state vector to denote how much of each value is superposed into the qubit. Right, so a classical bit state is written like this. I have 0 or 1. Right, there we go. Qubit state vector is written like this. I have something I'm going to call psi. We'd like to call wave functions psi. And it's this 2-element vector, alpha beta, where alpha times 1, 0. This is my basis vector, plus beta times another basis vector. And then we like to write it this way. We like to write this little funny 0 and this 1 inside these angle brackets. We like to use this kind of notation. For 0 and 1 are called basis states, and it happens to be in a basis that we call the computational basis. You can think of them like heads and tails on a coin, right? And we'll call 0 the 0 state, the 0 qubit, and 1 the 1 qubit, and let the basis be implicit. We're going to note that alpha and beta are complex numbers, which obey a normalization condition such that alpha squared plus beta squared is 1. So that's just a fact about these guys. We often construct visualizations of these states using something called the block sphere, which works well for visualizing single qubits. It doesn't work well for visualizing multiple qubits, but it gives you some sense for what alpha and beta look like by mapping those points onto a 2-dimensional surface. So it's best visualized as a point on a sphere. So we can look at like what does the 0 qubit look like on the block sphere, and it's something like this. And we've got these funny axes. I just want to pause and note. This axis goes from minus to plus. This axis goes from counterclockwise to clockwise. This axis goes from 0 to 1. So 0 to 1, that's our computational basis. So that's where here I am up at 1, or excuse me, the North Pole is up at 0, so 0 is up here, and then 1 is down at the bottom. These other bases, I'm not going to necessarily try to explain quite yet, but they're funny bases, right? So it's counterclockwise to clockwise, minus to plus, 0 to 1. We can look at the 1 qubit. The 1 qubit points to the South Pole. I'm going from 0 to 1 like so. Suppose you choose an arbitrary alpha and beta pair. Remember, they have to square, the sum of the square must be 1, so I'm going to make up an 80-20 qubit as like the square root of 0.8 times the 0. And I'm going to throw in an imaginary I of minus I times the square root of 0.2 on the 1, right? That's just to make that up. And those numbers, if you square them and sum them, you're going to get 1. So it's a valid pair of alphas and betas. And we can plot the 80-20 qubit, and that's just pointing off over here, right? So there you go. So for fun, later you should play with this, right? And try to draw some different qubits. And bearing in mind this alpha squared plus beta squared equals 1 really means, because these are complex numbers, that like the modulus, the sum of the moduli is 1. So alpha star alpha plus beta star beta is 1. So when you do the modulus of imaginary numbers, you use the complex conjugate. And I think you guys have seen that stuff in math classes, but if not, I just want to make sure that you know that the complex conjugate involves flipping the sign on the imaginary pieces. Okay. So measurement, we gotta talk about measurement. So these qubits, we can create them in superpositions of these states, but we will actually only ever measure them in the basis that we have chosen. They will only be measured in the 0 and 1. So an example of the basis is the 0, 1, Z basis we've been implicitly using so far, which is a convention called the computational basis. When you make a measurement of some superposition, you collapse the wave function. And you guys have maybe heard that kind of like stuff before in pop sci context. So if our original state was a superposition, it no longer will be post-measurement, right? It's going to be in the basis of our measuring device. And that what these amplitudes that we're setting out in front really tell us are the probability of measuring a result in this basis versus that basis, right? Or this answer in the basis versus this other answer in the basis. So for my 80-20 qubit, we have an 80% chance of measuring a 0 and a 20% chance of measuring a 1. So it's probabilistic. It's fundamentally probabilistic. It's a random, you set up a whole long string of these guys, you start measuring them, you're going to get different answers as you move along. If you measure enough of them, you're going to see, on average, you're getting 80% in the 0 and 20% in the 1, right? Which is different than like a lot of other sort of like computational tools that we're used to thinking about. We aren't necessarily used to thinking about computational elements that are fundamentally probabilistic. But in quantum mechanics and quantum computing, the elements of our computer are fundamentally probabilistic. And so, like I said, this is weird. I don't have time to go into how this was discovered, but later on, you can follow these links and you can read about, how people figured out that this is how nature works. All right. So quantum circuits. So we looked at classical circuits up above. Let's look at quantum circuits a little bit. So they're like our classical circuits, are composed of data lines and gates for operators, right? But there's some important differences. So you can't split lines in a quantum computation like we did in the classical one. We had a line and then we'd split. We had implicit fan outs, right? So we could copy. Can't do that in quantum. And then our quantum operators are unitary, which means that the circuits are actually reversible, right? So you can run the circuit forward and backwards. And that means that you can't, for instance, have something like 2 lines going into a gate and 1 line coming out, right? Because it's not clear how to run that in reverse. If you think about an AND gate, and I give you the result of an AND gate, you cannot always, or well, actually the AND gate is a bad example, but like with a XOR gate, you can't tell me implicitly, like, oh, I know that if this was a 1, that A was a 1. You don't know, right? You can't absolutely run it backwards. Quantum circuits, you can. So here's an example of a quantum circuit. So I'm going to input 2 copies of the ground state, or the 0, and I'm going to put them into this funny looking gate with an H. And then I have this other thing which is operating on 2 of these lines. And I'm going to explain what these symbols are later, but this is in some senses like the most quantum mechanical circuit that you can possibly write in this compact kind of form. The H and this crossbar are both quantum gates, which are the analog of our classical logical gates above. The H here is acting on 1 qubit, while the crossbar is acting on 2. This circuit's creating a bell pair, and I'll say more about what that means and what these gates are doing in a minute. But basically, this one is creating superposition, and this one is creating entanglement. We'll see more of that in a minute. Okay, so one of the consequences of this reversible computation is that our gates are linear operators. So, linear algebra is basically the foundation of quantum computing. It's the foundation of a lot of things. It's also the foundation of machine learning. Basically, it's really worth learning about. I remember in high school, that's where I first started learning about linear algebra, and I thought it was really boring. Super interesting. It's super useful. Really pay attention. So like classical circuits, we operate on quantum circuits with these gates, right? These gates mathematically take the form of matrices, right? I'm basically doing linear algebra. And acting with a gate is equivalent to multiplying our state vector with a matrix, right? So mathematically, that's how we think about these things. For single qubits, these gates are 2 by 2 unitary matrices. Now, I'm not going to get into what unitary basically means, but basically it means that it's norm preserving. So if I take a state vector and it has I have that alpha squared plus beta squared equals 1, right, requirement, which is really telling about the conservation of probability in some senses, right? Because remember, those amplitudes tell me what the probability of measuring the vector in different states are. My operator can't manipulate those probabilities such that you have a sum less than 1 or more than 1, because that doesn't make sense for probability. Right? So you need to know how to do some things with vectors. You need to know how to take the dot product, right? So if I have a 2-element vector, the dot product of A and B is just basically the product of the first elements plus the product of the second, right? And you can use this to define the norm or the length of a vector. I was using that language earlier, right? I can put these little bars around my A vector that denotes the norm, and that's A dot A square root. So the square root of A1 squared plus A2 squared square root. Hey, that looks familiar, right? This is the Pythagorean theorem, right? So if you have a 2 vector in space and you want to know the length of the vector, good old Pythagoras will tell you that, and this is an expression of that. You could derive the Pythagorean theorem from understanding how dot products work. So we can conveniently express inner products with this bra-cat notation. I guess I didn't use that word up above. I forget where I use it first in these notes. But remember, we had those little funny angle bracket ways of doing things. So you would define A dot B with a right angle bracket, or actually, this is blank. I forget if this is left or right. But you have the left angle bracket and the right angle bracket on these A and B, and that's the notation you use for a dot product. Our basis vectors, 0 and 1, are orthonormal, which means that they obey these conditions. So they are normal in the sense that they are they square to 1, but they are ortho. That's the orthogonal, means they're orthogonal to each other. So the dot product of these two guys is 0. There's no overlap. So, and therefore, if I have psi equals alpha times some 0 plus beta times some 1, I can do things like take the dot product of psi with itself, and I can write this out, right, as this alpha 0 plus beta 1 times alpha 0 plus beta 1, and I'm keeping track of which direction my bras and kets are oriented, and then I can use associativity to group those terms, and I come down to my alpha squared plus beta squared. So this is, we know this guy has to be 1, so this is another way of expressing our normalization condition. The alpha squared plus beta squared is 1, and how all that kind of flows through. So, okay, so there's a little bit about oh, and by the way, the reason we call this bra ket notation, and by the way, is because these things, when they're written like this, looks like a bracket, right? So this is what we would call a bra vector, BRA, and this is a ket vector, depending on which direction you're writing them. And there's a little bit more subtlety to that, but I don't think I need it for this lecture. Maybe I do. All right, so now for matrix multiplication, right, you need to understand how, like, if this was a gate, how this gate is operating on this vector, right, this state. And you can go look up like what the formula is for like deriving the different terms, computing directly these different terms in this vector over here that's the result. But the things to keep in mind, just the easy things to keep in mind, is that if you have an m by n matrix, you want to multiply it by an n by p matrix, the shape of the output is m by p, right? So there's some rules. That these two inner edges, here I have 2 by 2 by 2 by 1, those two guys in the middle have to be the same length. You can't multiply 2 by 2 matrix by a 3 by 2 matrix. You just can't do that. You can do 2 by 2 times 2 by 3, 2 by 3 times 3 by 2. I mean, you can do all these other combinations, but you can't have these guys in the middle mismatch. And then if you know what the size of the output is, then you can just drop those two in the middle. So 2 by 2 by 2 by 1 goes to 2 by 1, right? So I have a 2 by 2 matrix operating on a 2 by 1 vector. I get a 2 by 1 output. And then the way I think about how to actually do these computations is I imagine that I pick up the vector and lay it on its side and just drop it on the matrix, right? So I pick up this B1, B2, roll it on its side, and dot it with this row, right? So and that's actually what you're really doing is you're dotting row by row. So this first row, the first output over here is just the dot product of this row and my column vector. And then the next one is a dot product of this row and this column vector, right? And so that's not like a general formula, maybe that's easy to abstract to matrices of arbitrarily large size. But in life, you're not going to multiply matrices of arbitrarily large size, right? You'll go up to maybe 3 by 3, maybe 4 by 4 if people feel like really torturing you. But it's just not illuminating to multiply a 17 by 17 matrix and a 17 by 80 matrix by hand, right? You use computers for that. But you want to practice on like 2 by 1s and 2 by 3s and stuff like that, just to kind of like get the flavor. So you should go home and you should try to multiply 3, 2 and 4 minus 1 by 3, 5 and see if you can get that to work out. And then you could check it on a computer. Okay. So there's gates operating on vectors, right? So, okay, so then what about multiple qubits? All right, so we can describe multiple bits of state vectors as well. So a multi-qubit state might look something like this. So I have some vector 0, 1, 1, 0, 1. Well, we get lazy, we get tired of writing all the like bra ket things like that. So by notational convention, we just collapse that. So all those zeros and ones that sit inside one ket, right? Now, superposition means the mathematical space these vectors span grows exponentially in the number of qubits. So there's a 2 to the n popping up again, right? And there's some restrictions actually on what these values can be based on some normalization conditions, right? But when we say that the number of things that I need to write down, the number of terms I need to write down is growing exponentially, here's an example. If I have 2 qubits, right? So I have 0, 0, or I have 2 qubits, there could be some amount of 0, 0, some amount of 0, 1, some amount of 1, 0, and some amount of 1, 1. So this a squared plus b squared plus c squared plus d squared has to sum to 1. You can see if you had 3, that you would then have to have twice the number of terms 4, twice again, and so on and so forth. And that's what it looks like to kind of write out multiple qubits. And so we've already seen this thing of like, oh, what if I have 200 qubits? How big a number is that? It gets very big, very fast. There is still a normalization condition on these terms, right? So the sum of the squares of the coefficients has to be 1. So here, if I have this state vector, this is a legitimate state vector because the sum of the square of 1 over square root 2 is going to be half plus half, which is 1. That's great. Now, just a side comment again, I mean, this is covered up above in the section on superposition and entanglement. Here we have one state that's a combination of values. So based on this wave function, you can't say if the leftmost qubit is in 0 or 1. It's a combination, right? And you might think, oh, well, it really is in 1, and we just don't know which one it is. We have to measure. But that implies the existence of hidden variables, and it's beyond the scope of this lecture to handle hidden variables. But there are definitive physical experiments you can do to rule out hidden variables. So it's not that. It really is a combination of these things. Okay. So to write the state vector for multi-qubit systems, we need to know what a tensor product is, right? So this, if I have my alpha beta ket vectors written like this, what this really means is that I've tensored together these two guys. And this little 0 with the x in the middle is a symbol for a tensor product. So tensor products are not the same as regular multiplication. They have different rules. And in particular, you need a multiplication operator that if it took two element vectors, makes a 4-element vector, right? 3 qubits tensored together makes an 8-element vector, and so on and so forth. And again, you can go look up what the rules are for multiplying tensors together with tensor products in terms of like, you know, subscripts and postscripts and all those kinds of things. But we're not going to do big examples. You can just look at a couple of small ones and be fine for some simple quantum computing stuff. The tensor product for two element vectors looks like this. You take the second one and you stick it up against the elements of the first, and then you can multiply them out, right? So I have A, B, and C, D. Basically, it tells me take C, D, stick it up against A, take C, D, stick it up against B. There I go. A, C, A, D, B, C, B, D, right? So you could look at that. That looks like for 0, 0, 0, 0 is 1 and 0, tensored 1 and 0. Just take 1 and 0, put it up against 1. Take 0, put it up against 0, 1. This is just scalar multiplication. There's no special rules for that. It's just element-wise multiplication. So I end up with 1, 0, 0, 0. And that's what we call 0, 0. So that's a 4-dimensional representation for this 2-qubit state. I could also think of it as 2 individual qubits tensored together, right? And this generalizes to operators or higher dimension things and what I call the obvious way, right? And whether it's obvious or not, you can argue. But again, it's the same thing. I just take the second tensor and just stick it up against all the elements of the first tensor, and then there you go, right? So that's how you do that. So for exercise, you should go and do 0, 1 and 1, 1 and see if they work out kind of the way that you think. So you guys take a break at the hour about. This wouldn't be a terrible point. I could go another couple minutes. This isn't a terrible stopping point in terms of whatever material.
Yeah, I was thinking we could see if there's any questions from the room, or I could ask a question. Let me start. Actually, I was curious about this point, and I'll hand it to you to pass it over here. But so my first summer research, well, second one, the first one I did in physics was in the quantum computing lab. So it was basically building circuits, but like, you know, resonating circuits and trying to see how long it could hold the charge, or, you know, measuring the Q factor in a circuit. Okay. And then building a simulation, a numerical simulation. I mean, I was just curious about like the definition of a qubit, like fundamentally, like providing that. So, and I guess, yes, I mean, I guess a comment for the students, like, well, I was surprised when I started running quantum mechanics. There's a lot of matrix multiplication and stuff that's involved. So this is like when you start doing problem sets in grad school and stuff, and you're trying to, you know, figure out what happens if you take a state and manipulate it. It's all encoded in the matrix math that you may have started learning in your classes. You do apply these things that you learn. But I guess I don't know if you just talk about like qubits and why we study circuits, I guess, to study qubits.
So, well, okay, so a qubit is anything that has these properties, basically. Any quantum mechanical system that you can work with in this way. And there's a lot of different physical implementations of qubits. If you're talking about circuit resonators, you might have been talking about implementing a transmon, which is basically putting a particular type of like a Josephson junction on an LC circuit, and it creates a system, a quantum mechanical system, that gives you a two-level quantum mechanical object. What's interesting, if you look at a transmon, it actually has many more than two levels, but the spacing is such that the first two energy levels are easily accessible, and then the third one is much harder to get to. So you can treat it like a two-level system. It's actually more, but you can treat it like a two-level system. So the answer to your question kind of is that almost any quantum mechanical system that's a two-level system can be a qubit. And if you go look at different technologies, there's a bunch of different ones. I didn't show all of them, right? But you can use photons, where you can use left and right polarization. Those are two bases that you can work in. People use cold atoms, right, where you use the spin of the atom. People have you started using silicon dots, where you have defects in like an array of silicon atoms, and the defect has like a polarization to it, so you can manipulate that. So there's all kinds of different ways of implementing qubits, and it's actually not clear at all what the right quote-unquote best one will be in terms of scaling and usability and all that kinds of things. There's a lot of competition in that space right now. Question in the audience? So it depends on what your qubit is, right? So I work with superconducting qubits mostly. So this is basically done through, you do manipulation with microwave radio frequency pulses, right? And then to do the readout, you literally can like run voltages again across the device, and you can measure basically a response to that to a probe, right? It will show up as like a current in a device you're using to do measurement. I don't know if that question. Mostly I work at a high level of abstraction. I don't touch hardware that much. So all my hardware answers are going to be a little hand wavy.
Any other questions? Not, maybe it's, or I see one.
Thank you. So my understanding is that if we are able to build quantum computers progressively, they're going to be able to outpace classical computers in terms of their power by a great deal. Because of the difficulty of doing some of the measurements that you talked about, would we be able to, because our current computers are classical or linked together by the internet, would we be able to combine all of their computational power to be greater than that of maybe a few of our supercomputers? Computation is very difficult using all of their combined power. Power.
So a couple of things there. So one, quantum computers will be good in, well, okay, so there's some question, honestly, it's a research topic, as to what the real final computational power of a quantum computer will be, because we have to overcome a lot of problems with noise, right? So they're very fragile systems. The superposition and entanglement that we want to leverage are very fragile, and interactions with the environment can destroy those things. So we have to use some very fancy techniques to try to minimize the effects of that. And we're trying to build what we call a fault-tolerant quantum computer, so one which is able to overcome the effects of noise. And it's not obvious that we will be able to. Like, many people are optimistic. I'm pretty optimistic. There's good reasons to be skeptical, right? There's also good reasons to be skeptical about, like, even if you can build a quantum computer, how big can you really make it? How much can you really do with it? It's interesting to see. In the second part of your question, I'm not sure if you were asking about networked quantum computers or you were asking about networked classical computers. So quantum networking quantum computers is a very important and interesting area of research. And eventually we'll get to an application where we look at some of the stuff associated with quantum networking, because you can actually link quantum computers together in such a way that you're able to build a shared memory very naturally, right? So if I have multiple quantum computers, there are protocols which enable me to access the combined computational space of all of those computers, right? So that is a thing that people work on, and there's all sorts of cool stuff that you can do in that space. I don't know if that's really answering your question.
Thank you.
Yeah, okay. More up here.
All right, this will be the last one.
I was just wondering, why do qubits have to be so cold? Like,
So some do, some don't, right? So for the superconducting transmons, they need to be superconductors. So if you had a room temperature superconductor, that'd be great. You'd win a Nobel Prize, right? You're going to have all kinds of applications. But for the ones that we have now, they have to be chilled down to extremely low temperature, you know, millikelvin level temperatures, right, for the superconducting properties to emerge. It's also useful for dealing with noise, because if you had a transmon sitting at room temperature, you're sitting in a very warm photon bath, right? The thermal radiation around you is going to mess with your device. Other technologies don't necessarily require superconducting temperatures, like ion traps, right, can sit at room temperature. Now they need to be in a vacuum, right? And the lasers actually cool the individual atoms down a lot so that they don't move and they stay in the trap, right? But it can just sit out here at room temperature and be okay, right? You didn't have to cool that guy down to superconducting temperatures. So it depends a little bit on the technology, right? There's a number of different qubit technologies that rely on superconducting devices. Those definitely need to be cooled down. Some of the ones that don't require that. Okay, so where were we? So, all right, so we had made it through tensor products. So I think we have all the like basic math we need to finally start doing some things. So, so for quantum gates, right, we represented what our gates did using truth tables. For quantum gates, we're going to use matrices. Now, you can, of course, do matrices for classical gates also, but whatever the case. All right, so one example of a valid quantum gate is the NOT gate, which is also called the X gate, which I forget if I talk about later or not, but I don't think you need to worry about it too much right this second. And it looks like this, right? So you have zeros on the diagonals and ones off diagonal on a 2x2 matrix. Matrix, gate operations are formally equivalent to matrix multiplication. Multiple gates together are equivalent to multiplying the matrices together. So if I can write this out, you see the NOT gate flips one computational basis state to the other. So if I take X and operate on 0, 0, 1, 1, 0 times 1, 0, we do my little thing where you pick the vector up and you drop it, right? You're going to find out that you get 0, 1, which is the 1. And you'll find if you put X on the 1, you get the 0. And you can maybe see that in your head if you look quickly. This also implies, of course, that X times X equals identity, which you can also check by multiplying the matrices directly. So again, if you pick up the pick up the columns and drop them on rows in the obvious extension, you'll see that you end up with ones on the diagonals and zeros off diagonal. And this is the identity matrix. If you operate with the identity on any vector, you just get the vector back. Okay, awesome. So you should be able to work out, you know, from this and other things, be able to work out a multi-pair of 2x2 matrices, or n by n for that matter. But in practice, you never really will go over 3 by hand. You use a computer for that. Another important operator is the Hadamard gate. This was that H that I had was showing earlier, and it rotates computational basis states into superpositions. So this is what H looks like. It's 1 over root 2 times 1 and then minus 1 on the diagonal and 1's off diagonal. What does that do? If I say H psi and I'm multiplying it on the 0 state, for instance, then I get this 1, 1, 1 minus 1, 1, 0. I pick my 1, 0 up, I turn it over, I drop it down and do my dot products. 1 over root 2 just carries over. So you get 1 over root 2, 1, and 1, which is equal to 1 over root 2 times the 0 basis state plus the 1 basis state. This is a very famous state vector. It's called the plus state for this little plus sign here. And if you operate with H on the 1 and you do the math, you'll see that you get 0 minus 1, which is called the minus state. Now remember when we had we were plotting our block spheres and we had a minus to plus axis, that was one of the axes that we had to look at things. This is those pluses and minuses. That's what's being referred to here. Just like X, H is its own inverse. So you can go later and you can work out H times H, and you should find that it equals identity, right? And at some point, yeah, work out H times H just to prove that it's I, and prove that you know how to do 2x2 matrix multiplication. You can also look at these block spheres for some of these operations. So X times 0, we said was going to be 1. Sure enough, there it is, pointing down at the 1. Then H times 0, what does H times 0 do? It goes to that funny plus state. What does that look like? Well, here we are. See, this is why this axis is the minus and plus axis. that put my vector purely into that axis. Then I can also do h times the 0 qubit. H times h should be identity. This should just keep 0 qubit at 0 qubit. And there it is, still sitting at 0. Very exciting. Okay, 2-qubit gates. So the gate for a 2-qubit state is a 4x4 matrix, because my 2-qubit vector is a 4-element vector. The most important 2-qubit gate is the C0 or controlled NOT gate. And what that gate does is it applies a NOT. And this should be watch. This is how you edit marks down. Applies a NOT to the second qubit in the pair, but only if the first qubit is in the 1 state. C0 gate looks like this. You have 2 1s on the diagonal, and then you have 0s finishing the diagonal, and you have 2 off-diagonal 1s down in the bottom quadrant, right? Presented like this, maybe it doesn't make sense, but if you think about how 2-qubit state vectors are written, right, and I think these were exercises up above of 0, 0 is 1, 0, 0, 0, 1 is 0, 1, 0, 0, 1, 0 is 0, 0, 1, 0, 1, 1 is 0, 0, 0, 1. And if you just kind of stare at this, and you think about what this matrix multiplying these different vectors are going to do, even I think without writing it out by hand, but certainly if you write it out by hand, what you'll see what happens is that if the first element is a 1, you're going to flip the other one. And you can see that the bottom quadrant is the only active off-diagonal piece here. That's why it's going to hit just the guys that are living down here. And you can see it's going to flip them, because it's going to be like an X in that space. So, okay, the C0 gate is cool because it lets us generate entanglement. All right, so bell pairs and entanglement. So entanglement is super important. You know, the shortest way to think about entangled states is that you had multiple subsystems. When they're entangled, you can now no longer really describe them as subsystems, now an entangled whole, right? You can no longer explain the system as a sum of its parts. It has to be explained as its entirety. So one way to think about it is as an example. So many multi-qubit states can be written as a decomposition of single qubit states. So like 0, 0. 0, 0 is this 1, 3 zeros. I can write that as 0 tensor 0, right? So that's a fancy way of saying 0, 0 is made of 2 individual qubits in the 0 state sitting next to each other, right, in the notation. All classical states can be written like this, right? They can be a decomposition. But there are quantum states that cannot be decomposed. And those are what we would call an entangled state. For example, this state, 1 over root 2 on 0, 0 plus 1, 1 is 1 on root 2, 0, da, 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 plus 0, da, da, da. This 1 on root 2, 1, 0, 0, 1. You cannot turn this into a tensor product of single qubit states. Right? This qubit state we happen to call as a bell pair. It's in the bell basis. We'll get into a bit more of that in a minute. But there's no way you can decompose that to 2 single qubit states. So for fun, for an exercise, you should try. You should try to decompose this into 2 single qubit states that you could form through a tensor product, and you won't find one. And actually, the nice thing to do, of course, then is to try to write a proof that says that there is no such state. And then the other thing I mentioned is there's this forms a bell basis. There are 4 states in the bell basis, and this is one of them. And you should try to think about how you could find the other 3. Exercise to find the four vectors in the bell basis. All right. The last thing that you need to know for writing quantum programs is that there's no cloning, right? And so I'm not talking about this kind of clone in terms of the clone wars, but a very important property of qubits is that you can't copy them, right, in general. And this is a consequence of the no cloning theorem. And of course, if you know your qubit is in one of the basis states, after a measurement, for example, you can easily copy it by putting another qubit into that state if you want. But that's not really copying. It's just sort of state preparation. You can't copy an arbitrary qubit. And here's a little proof of that. So suppose that you did have some operator that could clone a state, right? That means that you would have some operator U, such that U operating on psi and this other state, which was prepared in the ground state, but holds for if it was in some other state too, equals psi, right? Turns out this can only work if psi, if this first guy, is 0 or 1, right? And everything hinges on the fact that this is a unitary operator, which means it can't change the norm. Here's a quick proof. So if I have some arbitrary state in psi, and I want to operate, and I want to try to make a copy of one of them, and I start with my other one in the ground, right? I can rearrange these terms. Because U is unitary, I can insert it into the middle here. So this is this U dagger. U is equivalent to the identity for a unitary matrix. right? And then my copy operation acts on to the left and then to the right. This turns into psi, or excuse me, phi psi, which is phi psi squared. So it's like saying that this copy only works if these guys are also 0, 0, or 1, 1, right? Because for this guy to be equal itself squared, you need it to work out that way. Okay, so, all right. Now we can start writing some quantum programs, right? And so here I am again trying to communicate with memes and GIFs. All right, so consider a diagram for a simple circuit. So had a motor in a single circuit followed by a measurement. How do you write a quantum program to run that circuit if you wanted to do that, right? So one of the ways you can do it is you can use a programming language called QASM, this QASAM. It's a very low-level way of writing quantum programs. Because it's low-level, it lacks a lot of the abstractions that would make writing large programs very convenient, right? So there's no type polymorphism or template metaprogramming or any stuff like that. It's very simple notation. But one of the nice things about that is that you can look at QASM and you can just read it. You don't need to really know anything. It's kind of obvious about how it works. Anyway, you can read more about QASM in some academic paper. It was invented by IBM. It's like QASM stands for Quantum Assembly Language, basically. So it's a very, again, minimal abstraction for that. Okay, so you have some Python code to run QASM strings. You can look at that later if you're interested. Create a program in QASM. You're going to write a special Python string that can cover multiple lines. And you do it like this. So you have some quantum program string equals triple quote, put your quote in, triple quote, and that's just the rule you follow to do a multi-line string in Python. Just how you do it. You would also use single quotes instead of double quotes, but whatever. All right, for the program itself, you need some boilerplate. You got to put this OpenQASM 2.0 and this include qelib.1.inc at the top. You just do that. You don't worry about it. You just do it. And then now we're going to do a little bit of coding because we want to do this H in a measurement. So we have to create a register, a quantum register to hold our qubit, right? And we have to create a classical register to hold the result of the measurement. And we have to operate with our Hadamard gate on the first element of our quantum register. So that's what this HQ0 thing here is, right? And then this is what the string looks like when we've got all that together, right? So this is the QASM program for that circuit I had just above of H operating on a single qubit followed by a measurement. Now, I said that QASM is very easy to read. Is it maybe not easy to write without looking at some documentation, right? Like if I hadn't shown this to you and I was like, okay, write a QASM program, you know, the likelihood that you would have come up with this correct syntax is low, but I do think this is easy to read, right? As long as you know what a QReg is and a CReg is, you know, you got an H on Q0 and you measure, you know, so you can read QASM, even if it's maybe a little tricky to write, and you can edit QASM, right? So if I give you some QASM and I say, change this circuit to do some other thing, pretty easy to do, right? So I charge with a relatively little thought, you can write quantum circuit programs following this type of using QASM, right? Okay, so we can run it. So I had created a function a little bit above and some hidden code. It lets us run one of these random strings. So what happens if we run it? So I measure a 1 513 times, and I measured a 0 511 times, right? And that's because I put a qubit into the H. I operated on H. I put it into an even superposition of 0 and 1. And when I did the measurement, it was probabilistic, right? I had a 50% chance of getting a 0 and a 50% chance of getting a 1, right? And I did 1,024 measurements. I happened to get 511 in the ground state and 513 in the excited. And you know, if you run this again, you'll get slightly different numbers, right? Because like I said, it's probabilistic. If you run it, you know, you can run it many times and and look at the statistics and you'll see that on average, you get half of the results in the 0 and half of the results in the 1, and that's just what that circuit does. Okay, very exciting. That's because we created, like I said, this even superposition of 0 and 1, and then we're measuring, so we're going to get this probabilistic outcome. We can look at other circuits, like so here's this Bell circuit I talked about earlier, which is H and C naught on these guys. You can kind of imagine, just based on what I showed you earlier, what the QASM is going to look like this here. Because now I have 2 elements in my quantum register, and I have 2 in the classical, and there's 1 extra gate. Maybe the syntax for the C naught gate isn't immediately obvious without sort of seeing it, but like you can kind of imagine what it's going to look like. There's this. I have a quantum register with 2 elements now, and a classical register with 2. Again, this is one of those things you know, I always assume that people know like very basic Python programming stuff or just very basic programming stuff, which sometimes is true and sometimes isn't. But this notation of I have like a letter and then I have these braces with a 2 in it, this is telling me the size of an array in a programming language. So like I have some vector or an array with 2 elements. This kind of notation with these square brackets is really common for that, right? So that's what this means. And it's a little bit funny because it's a little overloaded, right? Like when I declare my Q register, this 2 is talking about the size of the array. Later on, when I refer to it, these elements are referring to indices. They're referring to particular elements in the array. So this 0 is referring to the first element in my quantum register, and this 1 is referring to the second element in the quantum register. And this is very common in programming to see this type of like array notation. If you haven't seen it before, like if you go look at like a Python tutorial for an hour, like, you know, that kind of stuff will become clear. Anyway, so that's what's going on here. I'm creating a register, a quantum register of size 2, classical register of size 2. I operate with the Hadamard on my first qubit. X is the notation for the C0 gate, right? Because it's a controlled X gate, right? With my control being 0, my target being 1, right? And then I'm going to measure, and there's my chasm string. Okay, so now I can measure it. What do people think we're going to get? Just think about it for a second. I want to ask people to actually say out loud. I know if I did, everyone would just sit there silently. But think about it for a second what you think we might get. Let's run this. Turns out here we got 511 00s and 513 11s. Run it again. We got 522 11s, 502 00s. Run it again. And to run it, I just hit shift return right in this cell here. It's all I got to do to run that. But the point is, I'm only getting 00s. I'm only getting 11s. I'm not getting 01 or 10 ever, right? And you can verify that this simulation of the circuit is doing the right thing. The quote-unquote hard way was linear algebra, right? So the first step would act on H on qubit 0. This is so if you try to reproduce on your own, it's really a 2-qubit operation, right? It's really H tensor I because I'm operating on a 2-qubit system, right? That'd be the one thing I think that would throw people off if I told you to go off and write the matrices for this. And you wouldn't have known how to do the 1-qubit operation on 1 qubit when you have 2 of them. And the answer is that you want to think of it as like a single qubit operation tensored with identity, which is like a non-operation, right? And so if you do that, if you take C0 times H0, H on the 0 qubit tensor I on the second qubit on psi, starting in the ground state, you'd find this. Here's my C0 matrix. This matrix is Hadamard tensored with the identity on the second qubit. If you work it out, you can kind of imagine in your head even, if I have identity and I'm squishing those elements up against the other 2x2 Hadamard gate, that you're getting what you would expect, right? Because Hadamard was 1, 1, 1, minus 1. So then if I'm sticking identities to those things, this is like an identity block times the 1, identity block times the 1, identity block times the 1, identity block times the minus 1. You can see that kind of flows. You can multiply these 2 matrices together by hand with my usual thing about picking up the columns and dropping them on the rows, right? Pick up this column, drop it on this row. You can see that it's going to be a 1 is what we're going to get, and then pick up this column, drop it on that row. It's going to be a 0, right? And so you can multiply these 2 guys together to get one 4x4 matrix, and you can do it by hand, but you could also do a computer. 4x4 is getting to the point where it's just tedious, right? Anyway. So you could multiply all that out, multiply it by my initial vector, which was a 0, 0 ground state, and I'm going to get 1 on root 2, 1, 0, 0, 1, which is a 50% chance of showing up in the 0, 0 state, or a 50% chance of showing up in the 1, 1 state. Linear algebra version and the probabilistic programming version are giving me the same answer as you would hope, right? Okay, so finally we get to the IBM quantum experience. So writing CHASM is a fine way to run simple programs, but it can be a tricky way to get intuitions for like what gates do and how the wave function evolves. And it's actually a little tedious even to write out all those different things like that. So there's another tool that you can go play with a little bit later called the IBM Quantum Experience. And in order to use it, you need to create an IBM ID, but that's fine. You just need an email address, and then you can create a free account, right? And with this account, you have access to a cloud platform that IBM provides. It gives you Jupyter notebooks. That's great. So if you've been playing with Jupyter notebooks for this, that's great. And they have learning materials for learning Qiskit, which is their Python library for writing complex quantum circuits, but they also have a circuit composer, which is the thing that I'm interested in here, which provides a visual GUI for building quantum programs, right? So it looks like this, right? And if I go over, we can look at it live. Here I am logged in over on the, I'll make this not show. All right, so here's the quantum composer. I can go click on it, right? And it brings up this interface, which I'm not a musical person, but I think of this kind of like writing sheet music, right? So you can go and you can do things like give me a new one of these, and it's giving me, here I have 4 qubits. I can click on these guys and I can add and subtract them. So I can like add a qubit, add another qubit, or I could click on them and I could delete the qubits, right? And it's just telling me how many I have to work with, and I can drag gates out. So like I can do something like, let me get rid of these 2 qubits because I just want to do a 2 qubit calculation, for example. Drag out a Hadamard gate. That's kind of neat. Drag out a controlled NOT gate. Kind of neat, right? And that's creating that circuit that we just ran a second ago. One thing you think is kind of neat is it actually writes the chasm for our circuit over here on the side, right? And it's kind of cool. I can edit the chasm. I can go over here and I can take away that C naught, and it'll take it away over here. Or I can write the chasm directly, and it will add the gate in the composer. So that's kind of neat. Those kind of go back and forth with each other, right? Although, honestly, it's like way easier to write with the, these guys than with this one most of the time. There's also documentation. I forget exactly how you access it. Okay, so I can look at these that way. Also, what if I search for different operations? And they tell you the names of the gates like this. If you poke around a little bit, it's not hard to find documentation of these gates telling you what like the matrix representation is and what they do. It's just tricky to do in real time when you're doing a demo. Then I can also do measurements. Here's a little measurement. I can measure. It's got a little Z on it because I'm measuring on the computational basis. So I can measure 1 qubit. Does different things. And I notice there's these different things going on in the bottom, right? Like these probabilities move around as I add and subtract these guys. And this state vector coming out the other side is changing. You notice that when I add the measurements, let me take them away, right? It changes what the state vector is, because here I haven't measured anything, so my state vector is still existing as a superposition. Once I add the measurements, it collapses the state vector. So that's what's going on here. This Q sphere is a visualization. Remember I had the block sphere for single qubits? This Q sphere is a way of doing multi-qubit visualization. I'm not going to get into what that means. But this is pretty neat, right? I mean, you can kind of, without even like knowing a lot of programming, write quantum programs, and you can like add, you can keep adding stuff, right? And you have this, I have a 4-element classical register for what it's worth. You can add other gates, like I can add a Y gate, and I can add a C naught there, and I can add another Hadamard, and I can add a Toffoli gate, which uses a double controlled flip, and I can add an arbitrary rotation in X, and see it's got a little angle parameter in it, right? So I can change that. I want it to be a pi/4 rotation. So you can do all this stuff, right? And you can build these weird amplitudes coming out the other end. And this is how you write a quantum program and how you write a quantum algorithm, right? Like if you have some, this is not an algorithm that's computing anything useful, I don't think. This is just a random collection of operations. But what you would do if you're interested in actually doing a computation is organize these elements such that the probabilities that you're coming out with the other side here are constructively adding to the correct answer and destructively removing wrong answers. Right? Okay, so very exciting. Okay, so this is just back to this notebook. This is just a screenshot of this thing. They change the UI and they move elements around on the quantum interface constantly. Every time you log in, it's going to look a little bit different. So that's why I have some screen caps showing some of these different things. Notice that back when I made this screen cap, they weren't collapsing state vectors on measurements, which is kind of interesting. Okay, so the circuit composer does a couple of nice things for us. It gives us nice visualization tools for understanding the evolution of small number of qubits, lets us write chasm, lets us display the chasm for the sheet music style of writing things, right? So it's all very nice. You can even run the circuits on real quantum computers if you want to. So if you go back over here, right, so I can run this. I have a setup and run option over here. And I can choose to run on a simulator, right? But I could also go run on a real quantum computer if I wanted to. Like here's IBM Torino, has 133 qubits. And here's IBM Sherbrooke, has 127. Now, I'm being a little bit ornery because I, as a researcher, have access to some computers that you guys won't, right? So if you create a public account with IBM and you go and you just want to run a job on a quantum computer, you will not have quite the same list of computers that I have. But you still have some cool ones, I'm sure. I'm not sure what all they have in terms of in the public queue. They probably got like the 27 qubit machines, probably in the public queue. And the simulators, of course, will be. Anyway, I don't know. I actually don't know what all they're going to put in the public queue or not public queue. But it's kind of neat. You can go look at this. Let's say we want to run a job on Cairo. Here it is. They show you how the qubits are laid out. This matters if you want to do like a 2-qubit gate. You can only do 2-qubit gates between qubits that are adjacent. So I could do one between 7 and 10, but I can't do one between 7 and 12 easily. I can, but I have to do swap operations. I have to swap the quantum state of 7 and 10, and then do a 2-qubit operation, and then swap them back. Right? They tell you also about like the quality of the qubits here, right? So these guys that's a little bit more purple, right, are going to have more errors associated with them, right, due to noise and due to imperfections in qubit construction.
I had a question, Gabe.
Yeah.
So these are transmon qubits or
transmon
charged. So these are actually on a chip somewhere.
Yes, these are actually on a chip in a dilution refrigerator in upstate New York, and you can tell that little thing what to do. Right? You can click. I can select IBM Cairo, and I can run on IBM Cairo. So I just submitted a job to run this random gibberish on IBM Cairo. Right? Now then, okay, great. What does that mean? I didn't look at the queue at all, right? So if you want to run these guys, so there's a pending jobs of 150, right? So this job probably won't run during this lecture, right? You have to wait for everyone in front of you to run before it runs, right? If you want to see that particular one, right? But and that can be irritating to wait sometimes, but it's how it is if you want to run it for free. But okay, so here we go. Hasn't even shown up in the pending, which is kind of interesting. But I ran a couple of 2 days ago, right? I ran on a simulator. Now they were having trouble displaying the results. Yes, they're having some problem showing results right now. I don't know what the deal is. Buggy sometimes in terms of whatever they're doing. But I ran a couple of these, just a couple of days ago as a warm up. I ran one on a simulator. I ran one on one of the real machines, right? That's not what I wanted.
Follow-up question. So,
yes.
Well, usually the superconducting element on these is aluminum, or?
I don't know. Probably, yeah.
But they have to be in like the tens of millikelvin, I guess.
Yes.
How cold are these things?
Yeah, tens of millikelvin. That's right.
And I guess they're linked up. I guess the qubits. I guess they're actually on a line.
Well, they're actually in the little pattern that we showed, right? So, I mean, the connectivity is expressed in the graph. So if you look at Cairo, right, they're not actually on the line. They're laid out like this. Right? How they're actually laid out. And that layout matters for a lot of things, as you guys could imagine. If you can only talk to neighbors easily, right, then what the layout here is very important. And they've chosen this layout for what it's worth, this kind of weird looking layout, this heavy hex layout, because they have a philosophy on how eventually they're going to do quantum error correction. Right? But I'm not going to try to get into all that right now. But that layout is for a very particular reason. Okay, so as I mentioned, it takes a while to run if you want to run one. And sometimes looking at the results can sometimes be tricky. So here's a screen cap of a result from something that I ran on Athens, which actually isn't even available anymore. They don't even have the 5-qubit machines available anymore. They basically start at 27. Here was just some job running this Hadamard circuit, or this Bell circuit. And what's kind of interesting is the results aren't exactly what we predicted. Remember, we decided we were going to see only 0, 0, and only 1, 1. Right here, I've got 50. You got 50% in 0, 0, and 46% in 1, 1, and a 1.5% in each of the other states. What's going on here? And that's due to noise on the quantum computer. So noise is a complex topic that I'm not going to try to get into in depth. But the simple way to think about it is that it's very hard to isolate the computer from the environment, and it's very hard to make perfect qubits, and it's very hard to do perfect operations, and And superposition and entanglement are incredibly fragile things. Right? And so really the number one activity in some senses in quantum computing is thinking about dealing with noise. Because in order to eventually to get computers to do the things that we really want them to do, we need to solve that problem. Okay, so practical quantum applications. So this is a quantum teleportation application. So we have the traditional Alice and Bob sharing a pair of communication channels. They can transmit classical bits on one channel and quantum bits on another. And we're using this, this is practically accomplished using an algorithm called quantum teleportation, right? Which sadly is not quite as cool as beaming up in Star Trek. But it isn't science fiction. This is a thing we do at Fermilab, and you can go read about experiments that we do with quantum teleportation here, though. The basic game is Alice would like to send Bob some quantum information, but she fears there may be an eavesdropper. And so what we want to demonstrate is how you can use, if you're using a quantum channel, how you can catch eavesdroppers, not because of like you have better encryption or whatever. It's because physics, right? You can capture eavesdroppers because physics is true, right? So okay, so they have these two different channels, and the classical bits will follow an agreed upon code for a set of operations to perform on the qubits, right? So there is still a chance for espionage. You can, if you know what the classical code is, then you can get through that way. But Alice and Bob had to agree on how to interpret the classical bits in advance. But afterwards, all the information exchange is fully public. So this is going to be a public channel. They're not worried about like trying to, they will know if anyone listens, is the point of the application. All right, so all right. So here is the chasm string for the circuit that these guys are going to use. And it's a complicated circuit in some level, although it's not that bad. So you can copy and paste this chasm into the circuit composer to look at, which is pretty cool. I'm going to show it in the composer. Oh, here I've run it. Okay. So if you look at it in the composer, it looks like this. You have, there's a Hadamard on Alice's, and then she does a measurement, prepares it to 0, does a Hadamard, does a measurement. That's going to tell her what 2 random classical bits are that she's going to use to do her quantum encoding. Depending on what those quantum encoding is, she's going to do a set of operations on a qubit. She's going to send that qubit to Bob. Bob is going to have received the classical bits, so he knows how to undo the quantum operations that she did. That's basically what's going on here, is that she is going to generate a pair of random numbers using Hadamards. She's going to prepare a qubit to send Bob. She's going to send the qubit, and then Bob is going to decode the qubit. Right. There you go. There's the circuit. You can run the circuit in IBM in the quantum composer later if you want to. Right. And so note though that the comment code has the chasm taken out. I took the chasm out of the comment. Took the comment out of the chasm here. The reason it's worth doing that is that you can actually run the circuit with a little stepper. If you come back over here, there's a way to run but it's tricky to do this. I forget. If you poke around for a minute, it's much easier if you aren't doing this in real time. Run circuit step by step. Where is this guy? Where is he? I'll see if I can figure it out in a little bit. All right. Oops, I didn't want. It's kind of neat to like run through and watch the state vector change one by one as you go through. So okay, so if we can run that on the Quantum Experience website. Here I'm using the simulator and view the output, and I get some sets in like these different bases, and I say it's what we expected. There's a decoding in terms of Bob value, the fiber value, the Alice value, and then what is A? All right. Okay. So the A hat and A val, these are the code bits that Alice sent, and then this is what Bob is going to find, and this is what was in the fiber. And Bob is going to basically find 0. His leading 0 is what we expect to find if there were no eavesdroppers. Okay. So I guess you can run that code through the chasm through the composer. All right. So now let's put in a spy, traditionally named Eve, for the eavesdropper, and see what happens. So Eve is able to capture data in flight. She has a fully functioning quantum lab, so she can create and measure qubits and send quantum qubits and all those kinds of things. Right. So her goal is to capture and store sensitive quantum information. So if you do that, the chasm string changes to simulate the situation, because now there is an intercept. Right. So there's a spy intercept. She can't see the true quantum state, but she can make measurements, right, and then try to replace the quantum state based on those measurements. Right. So that introduces some modifications to the circuit. There's a measurement of the in-flight information, a reset. Depending on what Eve measures, she puts back what she measures. Like, did she measure a 0? She puts back a 0. Does she measure a 1? She puts back a 1, right? You can kind of see where this is going, right? Because she can't measure superpositions. She doesn't know the right basis to make the measurement in order to find the true value of the qubit, right? She can only measure in an arbitrary basis. Okay, so if you run this, right, now we have some leading 1s. These are cases where Bob did not find a 0 on the qubit, which is what he expected. Right? So if you try to run, as an aside, and I'll explain what all these different numbers mean in a second. If you try to run this on quantum hardware, it may not work. Like if you try to run this circuit that I have here, if you copy and paste that and try to run it on the quantum experience, and you try to run it on hardware, it may not work because we're using mid-circuit measurement, right? We're doing some measurements in the middle of executing the circuit and conditioning some things later in the circuit based on that. And that may not be a public API function for IBM. They're working on it, so it might be. I don't know if it'll work. It probably, but it will definitely work on the simulator. Okay. So this interpretation of all these results is a little bit subtle and requires walking through case by case, right? And I'm not going to like unpack all of the values verbally here. I mean, you guys will. It's just too long to go through all of it. But what I really encourage you to do is to think through these different cases and see what's going on, because it'll explain how the circuit is really working. So in the case of you measuring all 0s, what this means is that Alice doesn't apply a Hadamard or an X. She generated 2 0s. So the 2 0s on her 2 random numbers means that she just sends something in the computational basis, sends a 0. Bob gets those classical 0s from Alice. He doesn't apply any gates. Eve in the middle captures a qubit, measures in the computational basis, finds a 0 because that's what it was, sends a 0, so the spy isn't caught, right? And then there's different cases depending on what Alice does and what measurements are made, right? And if we look at one of the cases where she does get caught, in this case we have a 0 and a 1. These are telling us that those are the 2 classical bits that Alice sent. So she applied a Hadamard and sent a plus, right? So now she sent a qubit that was not in the computational basis state. Eve can only measure in the computational basis state, so she can't measure plus. She flip a coin, measures 0, right? She prepares 0, sends it to Bob. Bob gets 0, 1 from Alice, so he applies an H to produce a plus, and then he does a measurement, and he's got a 50-50 chance of getting a 0 or 1. Maybe he got a 0, right? In which case he wouldn't have caught her, but here he got a 1, but he caught her. He realized, there was a tampered with qubit in this message. Right? So the way to think about it is, if you wanted to send sensitive quantum information, you would append like a header, which would be a set of these spy sniffer qubits, right? You wouldn't send 1 qubit, you would send thousands of qubits. The first some number of them would be a check that was this message observed? Did anyone look at this in flight, right? So what's the chance of catching the spy with any given sniffer qubit, right? We can do some Python to query the dictionary that the simulator returned to us. And it turns out that like that code looks like this. And if you run it, what you see is that there was a 24, in this case, 0.6% chance of the times we sent the message, we caught the spy. It's exactly 25% theoretically if you do all the amplitudes written out, right? So each spy sniffer gives you a 25% chance of catching spy. Way to think about that is, okay, how many spy sniffer qubits do I have to send to have a, say, 99.9999% chance of catching the spy? How many do I have to spend? Well, the easiest way to solve that kind of probability problem is ask, well, what's not the chance of 1 catch or 2 catches or 3 catches or whatever. We just care about were there any catches. Think of that as 100% minus the probability of no catches, right? That's the easy way to solve that kind of probability problem, right? So if you send 1 qubit, you have a 75% chance of catching the spy. If you send 2, you have a 75 times 75 equals 56% chance of missing the spy, 44% chance of catching, da, 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 da. Every qubit you send reduces the chances of missing the spy, and the chance of the spy slipping through dropping by 3/4 of each qubit, right? So then we can do, like, ask Python to, like, go find the inverse thing numerically, and it turns out to be about 40 qubits. They have 40 spy sniffers, then they have a 1 in 100, or whatever, 1 in 100,000, 1 in a million chance of getting through, right? So you just have to decide what is, and you can see how that probability scales, right? As you keep adding qubits, right? If you go to 50, you get another decade, basically, of probability in your favor. So if you have a quantum communication channel, this is a pretty cheap trick to see if there are eavesdroppers. 2 classical bits plus 1 qubit sent about 40 times, right? So no, we don't care if the classical channel is observed in this example. Eve doesn't know what the numbers in the classical channel mean. Although, like I said, this is the chance for espionage, right? Like if Eve knew the classical code for how the quantum information was encoded, then she would be able to reproduce the quantum information in principle, right? But if she doesn't, then this is a way of sending information in the public that can be observed, and you know if it's observed or not. So anyway, kind of cool. All right, that is that for the lecture here. So the thing that where this gets really interesting is if you go play with this stuff, right? So I understand sitting here and listening to it may be interesting, may not be interesting. I don't know. You guys have lots of stuff going on in your lives. But if you were interested at all in any of this, then the cool thing to do is to go play with it, right? Go pull this down, and you can go play with all this stuff. And there's enough here that you can actually figure out a lot about how quantum computing works, right? And interesting problems you might think about solving with quantum computing. And as a fun aside, back in 2019, I gave this lecture at Saturday Morning Physics. And one of the students, this gentleman here, Avi Vidali, was interested and went and played with the notebook and had some ideas about stuff to do with quantum computing, and reached out to me, and we ended up doing some work together. And that work is published in Quantum Machine Intelligence, right, which is the same. It's published by Springer. This is the same publishing house that publishes Nature and a number of other exciting journals. So the point is that, like, if you're actually interested in this and you're actually having fun with it, quantum computing is at a place where, like, you can actually do interesting stuff now, today, right? If you're interested, you don't have to wait for, don't let school get in the way of your education, right? Just start doing things that you think is interesting, and you may have published research. So kind of neat. That's it. Okay, so there's questions if people, or I got time for questions if people want to ask.
All right, so let's thank the speaker. There was one question online which kind of tied into what you were saying. Well, basically, what's the application or real-world purpose of running the quantum gates and circuits in this notebook? Well, is it like a prereq for getting onto a more advanced machine, or, I mean, and also I think I was curious more broadly about asking what the application of quantum algorithms are, I guess, on a more global scale.
So the short answer to that question is that a really interesting quantum algorithm is going to involve substantially more gates than this, right, and more qubits, right? You're gonna, if you assume this in this representation, I'm not worried about error correction or anything like that. This is just, and I'm not here in this representation. I'm also not worried about connectivity, right? Like the way that this thing works, I can have these guys. I can edit this guy to where is it? One of these guys should be this guy. Why isn't it bringing it up? Right, it is. I'm not seeing it. I can change which guy. Right. I'm not worried about connectivity. I can just apply qubits wherever I want. So this, or gates wherever I want. This representation is a good way for thinking logically about quantum algorithms. Like I said, really interesting ones are going to involve many more qubits than this and many more gates, right? So like really interesting quantum chemistry problems will involve something on the order to really do a full problem of 1 billion gates, right? That's a lot of gates. Now, you're not going to write that program in the circuit composer by coming in and dragging the little gates in one by one to get 1 billion of them, right? A lot of those are subroutines where you're doing some particular operation that involves 1,000 gates, you know, many times and that sort of thing, right? But so real quantum algorithms are substantially bigger than this. This is for building intuition and for building pieces of those kinds of algorithms, right? So you can do, if you go read, you know, actually, if you look at the, whatever, this quantum learning thing, so if you go to the, this IBM quantum platform, which is where you sign in your IBM ID, they have a learning section. You can go look at a bunch of, and you can click on it. Hello. They have a bunch of stuff in here. And they have Jupyter notebooks that you can go through on quantum algorithms, and they talk about, you know, some very basic ones, like Deutsch's algorithm is one of the first quantum algorithms where someone was showing some kind of quantum advantage over a classical algorithm for doing something interesting. But you can go through these. These are all small algorithms that involve handfuls of qubits that are doing some computation, right? They aren't like the kind of computation that you're going to use to revolutionize the world, but they do illustrate the concepts, right? So that's kind of the way to think about it, is that when you're operating at this scale, right, what you're really doing is you are building intuitions and you are thinking about simple applications and whatnot. That's the answer. This is, you know, you learn the basics here. You're not going to write big, complicated programs using QASM because it's just not efficient to think at that level of abstraction. You want to think at a much higher level of abstraction. But you would then learn how to use the tools that enable you to do the equivalent of like for loops and things like that in quantum computing, right? So that you could take things that are many thousands of gates on many thousands of qubits and represent them in a compact way.